Hi class, welcome back. Today we're going to discuss 5.1, that is the natural logarithm function differentiation and its differentiation. The objectives are to develop and use properties of the natural logarithm function, and also to understand the definition of the number e, and then find the derivatives of a function involving the natural logarithm function. Now, some of this material may seem familiar, as we have seen in our college algebra course. Let's begin. Let's talk about the natural logarithm function, also known as the logarithm for base e. The general power rule for an antiderivative has an important disclaimer. It does not apply when the power is equal to -1. Consequently, you have not yet found an antiderivative for the function f of x equals 1 over x. In this section, you will use the second fundamental theorem of a calculus to define such a function. This antiderivative is a function that you have not encountered previously in the text. It is neither algebraic nor trigonometric, but falls into a new class of functions called logarithmic functions. This particular function is the natural logarithmic function. So let's define this new function. Definition of the natural logarithmic function. The natural logarithmic function is defined by ln of x is equal to the definite integral from 1 to x of the function 1 over t dt as x is greater than 0. The domain of the natural logarithmic function is set of all positive real numbers. From this definition, you can see that the natural log of x is positive for all x greater than 1, and negative whenever x is between 0 and 1 strictly, as shown in the figure below. So we want to observe this function here. If you notice here, the logarithm function, it's here, the natural log. If you notice, the value of the function is above the x-axis, meaning it is positive. It is 0 when x is 1, and it is negative whenever x or the domain is between 0 and 1. From this definition, you can see that natural log of 1 is equal to 0. Natural log of 1, right, when x is 1, the outcome is 0, because the upper and lower limits of the integration are equal when x equals 1. To sketch the graph of the natural log of x, you can think of the natural logarithm function as an antiderivative given by the differential equation. dy dx equals 1 over x. Figure is a computer-generated graph called the slope or direction. So these are just a bunch of slopes at every single point, or directional field, showing small line segments of the slope 1 over x. So if I move this graph to any position, this is how the behavior of the function will be. Anyways, the graph of y is equal to natural log of x, which is the solution that passes through the point 1, 0. The next theorem, there's some basic properties of natural logarithm functions. So this is where it seems more familiar or common with what we learned in college algebra. What we're saying is that the natural logarithmic function has the following properties. The domain of the log function is from 0 to infinity, excluding 0. And the range is from negative infinity to infinity. The function is continuous within the domain and is always increasing and is always 1 to 1. The graph is concave downward. As we can see here, the function is concave downward. Using the definition of the natural logarithm function, you can prove several important properties involving operations with natural logarithms. If you're already familiar with logarithms, you'll recognize that these properties are characteristic of all logarithms. Theorem 5.2. Logarithmic properties. If a and b are positive numbers and n is irrational, then the following properties are true. Property number 1. The natural log of 1 is 0. That means the log of any number, any long base, any number of 1 is going to be 0. Number 2. The natural log of a product within the log is equivalent to the sum of two logs. Natural log of a plus natural log of b. Number 3, the natural log of a to the n is equal to n times natural log of a. So the idea that we can move the power to a product. Number 4, it's known as the quotient rule, property of logarithms, which is natural log of a over b is equivalent to natural log of a minus natural log of b. I remind you that whatever is the numerator within the log becomes the positive log, and whatever is the denominator becomes the negative log. Let's practice this concept using example 1, expanding logarithmic expressions. So when we go from this direction to that direction, from left to right, we are expanding the logarithm. When we go from here to from the right side to the left side, we are compressing the logarithmic. So here, obviously, we are using these properties to get this result. So the natural log within, and then we have the natural log of 10 over 9. We're going to expand this for the purpose of practice this property. This would just be natural log of 10 minus natural log of 9, using property number 4. B has the natural log of the square root of 3x plus 2. Now, we don't have a particular property that deals with square roots, but we can see that we have a particular property that deals with power. So it makes logical sense to change this expression into a power form. That is 3x plus 2 to the power of 1/2. Now that we have a power, we can use property number 3, which allows us to bring the power to be a factor in front of the natural log. So this would become 1/2 times the natural log of the 3x plus 2. Next one, we have for C, we have natural log of 6 over 5. 6x is the numerator, so we're going to have the natural log of the numerator minus the natural log of the denominator. This is using property number 4. Now from here, we notice that we have a product within the natural log, so we can use now property number 2 to expand that natural log. Thus, we have natural log of 6 plus natural log of x, followed by the minus natural log of 5 that we already had. We can see that we could use multiple rules or properties in the same problem. Problem D. The natural log of the quotient between x squared plus 3 to the second power all over x cubed times the square root of x squared plus 1. Because the overall expression here stands to be a quotient of the numerator over denominator, the first step is to subdivide this or to we write it as a difference by using rule number 4. The natural log of the numerator minus the natural log of the denominator. I want to reinforce the concept of using parentheses whenever it's needed to clarify the reader that this whole thing is part of the natural log. Secondly, we're going to use 2 rules in one line. We're going to use the power rule. Well, actually, we're going to separate that one. We're going to hold on a second. We're going to expand this part of the natural log because we realize that there is a product within the natural log. Since there's a product, that will be this first times this, right? So we're going to use the second rule, which allows us to separate the natural log into 2 natural logs. Natural log of the first factor plus the natural log of the second factor. That was rule number 2. Now, it is very important, very, very important, that because the minus is applied to this natural log, that we must carry the minus and make sure that it is applied to the entire expression. That means that we must put some brackets to represent that concept. The next line will require us to distribute this negative to both terms, and in the same time we're going to use property number 3, which allows us to move the power as a factor. So this will be rule number 3. So this becomes a 2 times natural log of x squared plus 3 minus natural log of x minus 1/3 natural log of x squared plus 1. I want to make note that this 1/3 went to the second natural log, not to the first one. Why? Because by this rule, it only is this power is applied to this power is from this natural log, so it stays only at this natural log. Can we expand this further? Well, you don't have a product within the log, or a quotient, or a power in any of the 3 natural logs. So therefore, we have completed the expansion, and this is it. Now, if you notice, these are just those typical problems where we are rewriting the expression for the purpose at this moment to practice using these properties. These properties become very important when we are starting to solve equations or differentiate or using the antiderivatives, or also for word problems. When using the properties of logarithmics to rewrite logarithmic functions, you must check to see whether the domain of the rewritten function is the same as the domain of the original. For instance, the domain of the natural log of x squared is all real numbers except x equals 0, because I remind you that you can only apply the natural log of a positive number, and thus x squared will always be a positive except when x equals 0. What about this case over here? If we apply the property, if you apply one of the power properties of the natural log, it allows us to move this power as a product, creating a different domain for the log. We know that the domain for this log is going to be x greater than 0, so it is not consistent with the original function. So we gotta be careful when we apply these rules to make sure that we understand what the domains of each function is. Alright, so we're going to move on to the number e. is known as a infinitesimal value that it can be described as the base of a natural logarithm. It is likely that you have studied logarithmics in algebra courses. There, without the benefit of calculus, the logarithms would have always been defined in terms of a base number. For example, the common logarithms have the base 10, and therefore log base 10 of 10 was 1. The base for the natural logarithm is defined using the fact that the natural logarithmic function is continuous, is 1 to 1, and has a range of negative infinity to infinity. So, there must be a unique real number x such that the natural log of x equals 1, as shown in the figure. Now, I want to remind you that this natural log of x, it is also a logarithm of some base. Sorry. So, the question is, what is going to be this base? This number that we are looking at is going to be denoted as e. And it can be shown that e is irrational, and it has the following decimal approximation: 2.7182818284, and it goes on forever. So if we use the fundamental theorem of calculus, we're able to rewrite this area using the boundaries from e to e, and this will give us the value will equal 1. So this gives us the next definition of e. The letter e denotes the positive real number such that the natural log of e equals 1, and thus is going to be the definite integral from 1 to e of the function 1 over t dt, which equals 1. Once you know that the natural log of e is equal to 1, you can use logarithmic properties to evaluate the natural logarithms of several other numbers. For example, by using the property that the natural log of e to the n is equal to n times natural log of e, and natural log of e is equal to 1, and n times 1 is n, then this proposes that you can evaluate the natural log of e to the n for various values of n, as shown in the table below. For example, if you're evaluating the natural log of x, where x is 1 over e to the third, then this will be negative 3. 1 over e squared will be negative 2. The natural log of 1 over e will be negative 1. The natural log of e to the 0 will be 0. The natural log of e will be 1, and natural log of e squared will be 2. And so we are able to rewrite this or help us graph this function. So logarithms shown in this table are very convenient because the x values are very easy to interpret. They're just a few integers, powers of e. Most logarithmic functions are, however, best evaluated with a calculator. For example, the natural log of 2. If we want to find the natural log of 2, we will have to turn on our calculator, find the value of e, and I'll use this calculator for now. If you guys notice, there is a natural log expression, and I'll just have to type in 2. Close the parentheses, and then press enter, and that gives me 0.6931. Alright, so we'll minimize this for now. And so we're gonna write here, this is approximately 0.6931. Let's try the next one, the natural log of 32. So we'll do the same thing. We're going to press the ln, type in 32, press enter, and we get 3.4657. Just to be more proper, I'll put an approximation symbol. Then we can also do the natural log of 0.1. Natural log 0.1. And that'll give us negative 2.302585, and so on, right? I'll be more specific if we need to evaluate this to a particular decimal. Now, if you guys notice, we were able to evaluate, I want to make sure that I make this clear. We evaluated non-negative, or in other words, positive numbers. So I want to make sure that you guys see what happens when you plug in the natural log of 0. When you do a log of 0. When you try to evaluate a log of 0, let's see what happens. Log of 0 is going to be error, because it's outside the domain. What about a negative number? If you try to evaluate if you try to evaluate the logarithm of a negative number. Okay. We also get an error because it's outside domain. So we can see here we can use the calculator to help us express or find specific values of logarithms when we cannot use logarithm properties. Okay, so that was a quick brief review of some of the properties that we defined in a previous class. So we want to actually point out a few things from here. One of the main things that we want to point out is that we already have sort of built a value for the antiderivative of 1 over t. We'll get to talk about more about that. And then sort of over here as well, we're starting to build that up. All right, so let's talk about the derivative of a natural logarithm function. The derivative of a natural logarithm function is given in theorem 5.3. The derivative, the first part of the theorem follows from the definition of the natural logarithm function as an antiderivative. The second part of the theorem is simply the chain rule version of the first part. So we are trying to define what is the derivative of the natural log. Notice that we never actually talked about natural log before this section, and so when we do the derivative of the natural log of x, this will be 1 over x for x greater than 0. Now, in most cases, remember that we also could have a function inside a function. So whenever u represents a function of x, and this is within the natural log, the derivative of this will follow the chain rule. That is, the derivative of the outside will be 1 over the inside. Whatever the inside is will be copy and paste here as a denominator. And then we'll come back, and then what does the chain rule say? Multiply the whole thing by the derivative of the inside. The derivative of the inside is derivative of u in respect to x. In other words, the derivative of natural log of u will be u prime over u. The derivative of the inside over the inside. Let's practice this concept. Example 3. Differentiate the logarithm function. The derivative of this function in respect to x of the function natural log of 2x. So 2x is the inside function. The rule says to take 1 over the inside. 1 over the inside multiplied by the derivative of the inside. Derivative of 2x is 2. So 1 over 2x times 2. The 2's will simplify and cancel each other out, giving you back 1 over x. Neat. Let's try this again. The derivative of natural log of x squared plus 1 in respect to x. This is clearly your inside function. So the rule says that first do the derivative of the outside, which is the derivative of natural log is 1 over its inside. At the end, you multiply by the rule of chain rule, multiply by the derivative of the inside, which gives you x squared plus 1 prime. The derivative of x squared plus 1 prime is 2x, and you multiply it to whatever you already had. So therefore you have 2x over x squared plus 1. Neat. So now what we're going to do here is we're going to combine other properties from the derivatives, such as product rule for derivatives. So let's find the derivative of the product of x times natural log of x. Well, using the setup of a product rule will be the first function times the derivative of the second function plus the derivative of the first function times the second function. So this is the product rule. But now when you go back and do the derivative of each one, the derivative of natural log of x is 1 over x times the x that you already had plus the derivative of x is 1 times the natural log of x. These will cancel each other out, so we're left with 1 plus 1 times natural log of x, which is 1 plus natural log of x. Okay, so the next example is asking us to find the derivative of a function inside a function. If you notice, we have a natural log of x being cubed. Now we gotta be careful, because these two do not mean the same thing, right? This means the whole thing is being cubed, versus this one means that the x is being cubed. And this one, you can use the the power rule for logarithms, right? The property of algebra that allows us to put the 3 in front. This one doesn't, right? This one, what we're going to do here is we're going to use, to find the derivative of this, we're going to use the power rule. So we're going to bring down the 3, leave the inside as it is, subtract 1 from the power, and multiply by the derivative of the inside. So the first example, we still have 3 times natural log of x squared times 1 over x. Multiply those together, and we get this. And that's it. So we observe a few examples where we have to find the derivative using the natural log. Now, I can ask you for other type of problems such as this ones, and we should be able to find these derivatives using previous properties that we have discussed in this section from this course. Alright, on occasions it is convenient to use logarithms as aids in differentiation non-logarithmic functions. This procedure is called the logarithmic differentiation. For example, I'll try this problem here, number 4. practice 4, we have natural log of x plus 1 to the 1/2. Right, so that's the same example. Let's find the derivative of this. Now, before I do that, I realize that if you notice, this is the outside function, and inside this natural log, there is a function inside another function. I don't know, have you guys counted here, but you already have a function inside a function inside a function. Too many functions inside a function. That means you have to apply chain rule that many times. So what we are suggesting here is sometimes simplifying the expression. For example, we know that by using algebra and some of these cool properties of logarithms, it allows us to rewrite the expression as 1/2 times the natural log of x plus 1, taking the derivative of this, right? We haven't taken the derivative, we just use the power rule of logarithms. Now, to finish this up, notice that this 1/2 is basically a constant, and all we have to do is multiply that constant to the derivative of this. So this will be 1/2 times the derivative of natural log is going to be 1 over the inside of the log multiplied by the derivative of the inside. Well, this is merely or barely just 1, right? So the final result will be 1/2 times 1 over x squared, which would be 1 over 2 times x plus 1, because this is just equal to 1. All right, you guys can try the second one and do some similar argument for that. All right, so let's work on example 6, where this allows us to use to find the derivative of this much quicker and better than what we would have used with basic algebra. If I ask you to find the derivative of this function, then if you guys notice, obviously we would have to use quotient rule, and at some point we would have to use power rule. What we are suggesting here is, what if you try to use some logarithm properties, but first, in order to use those, you must have logarithm functions. So we will apply the logarithm on both sides of the equation as a way to have logarithm functions, and we can do that as long as you do the same thing on the left as you did on the right side. Now, because this is a logarithm function now, we are allowed to separate this into two terms, two different logs, the logarithm of the numerator minus the logarithm of the denominator, using the quotient rule property of logarithms. Because we have powers, right, then we can use the power rule for logarithms, which means this becomes a 2 and this becomes a 1/2. And then we're going to go ahead and now at this point, this will be much easier for us to take the logarithm. So we're going to apply the logarithm on the left side. The derivative of the left side will be, using implicit differentiation, it will be the derivative of natural log is 1 over its inside multiplied by the derivative of the inside. For the right side, it becomes 2, which is a constant, times the derivative of natural log of x minus 2, which, as we know, is just going to be 1 over its inside times the derivative of the inside, minus 1/2 times the derivative of natural log of x squared plus 1, which is 1 over its inside times the derivative of its inside. So if you notice, this just was 1, this was just 2x, and we can start simplifying some of the expression. Now, what we're going to do here is, now we're going to go ahead and multiply both sides by 1, for the reason that we are trying to find y prime. So we don't need y in this case. We need to remove it. So we're going to multiply it on the right side. So basically we already have a part of the answer here. All we got to do is rewrite y in terms of x, because our answer needs to be in terms of x. So we do know what y is. Remember that where we started with, y is equal to this whole thing. So I'm going to go ahead and replace that in here. I'm going to put some highlight here. That's this part right there. And now we have this product. Our suggestion would be now to find a common denominator for this, and I sort of did that right here. Right, we found a common denominator for the first expression here. Maybe we'll put this highlighter. This right here is this by using common denominator, and this is over there, right? By doing that, we're using some algebra. We are able to put it all together, right? And real quick, I'll just mention how we did that. This needs to have a common denominator, so we're going to multiply this one by x squared plus 1. This needs to have an x minus 2, so we're going to multiply this by x minus 2. So both denominators have the same thing. This needs to be distributed. This needs to be distributed. And then when we multiply this part with this part, one of the squares will cancel with x minus 2. And then we're left with this one and that one that we're going to multiply to each other, giving you 3/2. And then we simplify the top, and that gives us 2x squared plus 2 minus x squared plus 2x, and that will simplify to be just x squared plus 2x plus 2. And there you go, we found the derivative. Now, it's not the most traditional way to do it, but it was a very clever way to do it. We end up getting the same result as before. Okay, moving on to the next example. Because the natural logarithm is undefined for negative numbers, you will often encounter expressions of the form of natural log of u. The next theorem states that you can differentiate functions of the form y equals natural log of u, as though the absolute value notation was not present. So differentiate involving absolute values. If u is differentiable function of x such that u does not equal 0, then what we're going to do is the derivative of a natural log absolute value of u will be u prime over u. Let's see an example of this. Let's say I ask you to find the derivative of natural log of cosine of x. Now we know that cosine of x could be negative, but what the absolute value is doing is making this always be positive. So the derivative of natural log is going to be 1 over its inside, multiplied by the derivative of the inside. The derivative of cosine is negative sine of x, so then we're left to multiply those together, which gives us negative sine of x over cosine of x, which is negative tangent of x. So we just found out the derivative of natural log of cosine of x is negative tangent of x. Alright, so I hope you guys find this helpful. This was a very quick section. Barely we introduced the properties of logarithms, and we introduced the derivative of the natural logs. And that's where we're going to focus, right? We want to make sure we feel comfortable finding derivative of natural logs from now on. In particular, be able to master the condition where you have to apply chain rule, which is the general form. I hope you guys find this helpful. Please let me know if you have any questions. I'll see you guys next time.